Hello everyone, my name is Aneta Wiśniewska and today I will be talking about examination of magnetic helicity and plasma oscillations basically, and prior to C-class flares. Okay, so first I want to start what type of oscillations we have in the Sun. So the waves are present inside the Sun and as well in its atmosphere. So basically we can distinguish between P modes, G modes, and fundamental mode, which is kind of known as a surface mode. Then we have also MHD waves and galvanic waves, which has more magnetic origin. And of course, in the solar photosphere, we observe mainly acoustic oscillations, and the 5-minute oscillations are driven by near-surface turbulent convection. And typically in helioseismic research, we create like kind of power spectra, which is showing us the most dominant periods or frequencies which are present at the level of the solar photosphere. However, in the chromosphere, the waves are changing their nature, I would say, and then we observe more MHD waves and galvanic oscillations. So this periodic oscillations can be detected, for instance, by line broadening. And when there is no intensity oscillations, we can interpret it as torsional galvanic waves. And we have some data which are showing us how they are propagating from the photosphere to the chromosphere. And this was already published by some colleagues already a long time ago. But we have also different classification of solar oscillations. And oscillatory behavior is also observed in active regions. So we can identify there short period oscillations, which are basically last 3 and 5 minutes about. This is like this range. Then we are talking about the long period oscillations. These can last even several hours. And then we identify ultra long period oscillations, and those persist for days. So as you know, the magnetic field basically has its origin inside the Sun. So only it comes, let's say, to the outside part of the Sun, to the solar atmosphere, through the active regions, which we can observe. So there is a link between a magnetic field and oscillations, actually, because magnetic field strength and morphology changes during solar cycle. From the other hand, internal solar oscillation is present constantly in time inside the Sun. We observe, although some lower frequency, dominant frequency at the solar minimum. However, this is still present there. So in active regions, we observe much higher frequency of oscillations when compared to the quiet Sun regions. And this is because basically, active region like a sunspot has magnetic structure and magnetic field topology, and which is, of course, has an influence on the propagation of oscillations. So in the chromosphere and corona, the waves propagate basically along the magnetic field lines. And on this cartoon, we can see how fast they are propagating, like let's say inside the sunspots. So this is the umbra region and penumbra region. So basically the waves which are propagating inside here, they are reaching very quickly the chromosphere, from photosphere to chromosphere. However, when we are moving a little bit far away from the umbra, and in penumbra the waves are slowing down to reach the chromosphere because of this structure and topology of magnetic field. So basically they are kind of trapped there. And some time ago already, it was a pilot study done by Manswe in 2016 actually. And this is this work. So they did some, sorry for this pointer. They did some pilot study, and they were just calculating the biospectral density from the gong data in the flaring region, and they observed that there was like an enhancement in some certain frequency range. So they showed that there is a big enhancement of the power in a range of 1 to 2 millihertz, actually. So I kind of repeated this investigation, but using the different data taken by the Hellrate instrument at the VTT. It was already a long time ago, it was 2019, but we were also able to observe enhancement of the frequencies prior to the flare. So before, let's say, at this frequency range 3 to 4 millihertz, it was not observed in the region of the flare, and then after, it was definitely the frequencies and the power of it were changed. Okay, so I did this study for many spectral lines. So here we have 7 different spectral lines, which indicates 7 different heights in the atmosphere. However, I see that I don't have much time to show you. What I wanted to show you is that really, if you look at the range of 8 to 9 millihertz, we can observe the change before the flare and power distribution of the oscillations at some frequency ranges after the event. Not so long time ago, because in 2020, my friend Mariana Korsos did some investigation on actually magnetic helicity oscillation and the evolution of the 3 magnetic helicity flux components. And she found out that there is some special oscillations that can be found in the regions in which occur the eruptive events, and which are not present actually in the active regions, which doesn't show such a eruptive activity. So we took the same, actually the same event that I showed you before, and we checked these regions, and we created a wavelet power spectrum to identify the helicity oscillation in this region. So we identified basically 3 to 8 hour periods which were present in this specific flaring region, and both were present before and after the flare event. And actually, this black lines indicates the position and the time of the 3 events that were happening. To kind of cross-check this with AIA data, I calculated wavelet power spectra in 3 dimensions to identify whether this is what we see in helicity oscillation is true. So we also detect the same range of the oscillation in AIA 304 channel. And then I created like kind of a 3-dimensional wavelet power spectrum to investigate this oscillation range in time. So we can just basically locate this pulsation, let's say, inside this data cube and inside this region. So you can clearly see how it's moving within time. So I think that it's one slide is missing maybe, but okay. So our conclusion is that we found 3 to 8 oscillations period, our oscillations, and near to the region where the flare occurred. Actually, it was more studies done in this direction, and we want to implement machine learning to improve more of such studies. And oscillation in the lower solar atmosphere prior to the 3 C-class flares even suggest that varying oscillation properties in a solar active region could be an indicative parameter for future flaring activity. And if you want to check our publication, there was like one from the 2019 in my publication, and the very recent one which was published actually yesterday. Okay, so thank you very much for your attention.